Morning, everybody, and welcome to Lugano, also from my part. I prepared the talk based on abstracts that I sent to Thomas Schönemeyer, and then afterwards realized that I may give a talk that may look a bit strange to you, because I'm sure you expect from director of a center to talk about large machines. I am going to talk more about some of the things that concern us in, I would say, generally in computational science in Switzerland, namely co-design and separation of concerns. And you will see in the end it's new separations of concerns. Maybe some of you who know me know that I have always a little bit different views about things. But I hope this is okay. So the thing that I guess keeps everybody excited in this field is this exponential growth of performance. When Jack Dongara gives the talk, he would show the impact performance. I am coming from the application side of the world, so I'm more excited about application performance, but the two curves roughly follow each other. We have a factor 1,000 increase in performance every 10 years since about, most of us in this business were, I was an undergraduate student. There's many people now who are students or work on our systems who were just about born around that time frame. So we've, for all that we can remember, things have been going at this pace. And so we would, of course, expect that this continues and that we will have an exaflop by the end of the decade. The things that make us a bit nervous are, of course, the factor 100 increase in concurrency that we see in the last 2 decades, and for things that you, of course, know, like Powerwall and things like this, we expect actually this to accelerate. The other thing that concerns us is this continued increase in power consumption, going from 100 kilowatts some 10, 15 years ago to megawatts to probably tens of megawatts by the end of the decade. And CSCS, like many other centers, had to basically, we moved into a new facility that can support this type of, not 20 to 30, but order 10 megawatts or more in power. So we don't just invest in computers, we have to invest in buildings. And another thing that we observe is this shift from custom-built processors to or high-end processors that are specifically designed for scientific computing to commodity processors that are now used in scientific computing. And Jaguar was one of the first machines to be at the top of the top 500 list based on and was fully based on commodity processors. So the first question that you ask, looking at these trends and concerns, is how well can applications deal with concurrency? And the other one is how efficient are they? Okay. Now it turns out, surprisingly, applications do rather well, and they did very well in almost from the beginning when this machine at Oak Ridge was up. This is a list of applications that basically show you have in many areas, including weather, combustion, seismology, chemistry, material science, biology. You have applications that scale to 100,000 plus cores. The thing is about efficiency, that there is more than an order of magnitude discrepancy between the highest performing applications and the lowest performing applications in terms of floating point performance. Now you can say, well, we should not be obsessed with floating point performance, but before we make that conclusion, let's look at why these perform the way they do, and particularly why these get so high performance. So I will now, in the next few slides, I will look at this one, DCA++, which ran very close to peak performance at the time of, Jaguar had around 2 petaflop performance. So this was a mixed precision algorithm. So peak performance was not very well defined, but it was doing very well. The application is a Monte Carlo application, and I'm depicting this by, trying with the zigzag, try to demonstrate, the stochastic, the random walk through some high-dimensional space, and where you propose a move, you make a move, and once a move is accepted, you have to, in this particular Hirsch-Fey quantum Monte Carlo algorithm, you have to perform a rank 1 update on a Green's function matrix. And so this is a BLAS 2 operation, and you can imagine this did very well on vector computers when the algorithm was invented in the 80s, but did poorly on scalar processors. And these were the ones we were dealing with at the time. And then it was a mathematician colleague who proposed to change the algorithm, and they laid this update, transforming a rank 1 update into a rank k update. This could be done without changing the complexity of the computation, but incredibly increasing the efficiency. Now, this is a plot of time to solution with mixed precision or double precision. In both cases, you see drastically coming down as you increase this delay. And the reason we see this incredible increase in efficiency is because when we look at the arithmetic intensity, what we see, the original algorithm had an arithmetic intensity, which is the ratio of floating point operations to data transferred, that is of order 1 and does not change with a problem size. And the new algorithm has one that scales linearly with this rank k, or the number of the number for the delay. And it is basically this change, this increase in arithmetic efficiency or increase in data locality that leads to an order of magnitude change in efficiency. Now you can do this analysis for various algorithms, elementary algorithms like matrix multiply, Fourier transform, matrix vector, or sparse linear algebra, and categorize the arithmetic intensity by order 1, order log n, or order n. And then look at the applications that use these templates, and then we find LIMPAC to be squarely over here. And since we build computers for this type, for top 500, and you can ask whether that's reasonable or not, but I know several centers in Europe who are really make that the main game. And so then you have to expect that applications that fall in this range will do well. Other applications like this Hirsch-Fey quantum Monte Carlo, before the algorithmic change, do poorly in the efficiency, but then given that we could change the algorithm, suddenly do very well on these machines. But then the lowest performing, like S3D Wharf or Cosmo, that I'm now going to talk about, don't do as well for purely algorithmic reasons. So I said something about data locality, and I will come back to this, okay? Now let me tell you why this is a key thing that we need to look at anyway if we are interested in power efficiency. And this is a slide I borrowed from Steve Scott, who was then at Cray, with the question, what takes more energy? To perform a fuse multiply add of 64-bit precision, or to move the 3 operands that you need, without which you cannot do any computation in the floating point unit, move these operands across the length scale of the silicon die of the processor. You have to bring the data at least from the edge of the processor to the floating point unit. It turns out in 2010, and this number has changed, of course, moving the data already in 2010 moving the data took a factor 3 more in energy than actually doing the computation. So this is the main reason why you want to really think about what you do on a computer and minimize data movements. This number is now bigger, of course, because the efficiency of the compute units keeps getting better and better. So the real problem is we have to think about this data locality, and this, of course, raises a question about, does now an application developer have to know about everything suddenly? And so let me, before I go into answering this question or trying to answer the question, let me give you a few examples now of how applications developers go about this. And the first one I'm going to discuss is this climate and meteorological modeling code COSMO that is used by 7 weather services in Europe and about 50 universities. It's a key code for us at CSCS because it's the model that Meteo Swiss is using for the operational weather predictions. And this is how it runs at CSCS. We take data from ECMWF, from a global model that comes twice per day, that is fed into a 7-kilometer model and perform 72-hour forecasts. And then this is fed into a 2-kilometer model where they do the 24-hour forecast, and this is run 8 times per day. So we have like a 3-hour time window to run the simulation, prepare the data, run the simulation, and then do all the analysis, and Meteo Swiss is then delivering a number of products from these. The model itself is solving PDEs, Euler equations, non-hydrostatic Euler equations, so it's a rather complicated model, but essentially PDEs on a structured grid. The grid has a physical feature, namely it consists of a you can view it as a 2-dimensional grid of columns. The grid spacing inside the columns is much smaller than between the columns. And this introduces a stiffness inside the columns and leads to favoring splitting up the time integration into an implicit solver inside the column and an explicit solver for the horizontal integration. This allows the horizontal integration to have a much larger time step because all the stiffness is basically absorbed in these implicit solvers here. And so this leads to a rather efficient computation, but it makes things tricky from an implementation or from a computer science, or tricky, I would say interesting from a computer science point of view, because we have now 2 competing motifs. We have a tridiagonal solve that favors a column-first data format, and we have a normal stencil computation that favors a storage by plane-first data format. And these 2 are in competition with each other, and it turns out now you want to, depending on the architecture you are on, you want to either use this one or this one, but you can't use both at the same time. So one will be favored, the other motif will be hurting. The code itself presents itself as follows. It's about 250 to 300,000 lines of Fortran code that splits up into about 20% in the dynamical core that takes about 60% of the runtime. Another 20% of the runtime is spent in the physics. And then there's other infrastructure. For example, assimilation is a large part of the code, but only a very small part of the runtime. So it is natural that we focus on physics and dynamics. And so now what we are showing is just typical bits of code, so simplified pieces of codes that represent the algorithms inside of the physics and the dynamics. and we can figure out arithmetic density, and we find that this here is arithmetically dense and therefore compute bound naturally in the physics, so we have to worry less about this in terms of efficiency, but we have to worry a lot about dynamics. And here we have 60% of the time spent, so we have to look at this. And what you can now do if you have these representative pieces of code, you can run it on various types of architectures. Here I'm comparing Interlagos to Fermi, the physics and the memory-bound dynamics, and you see clearly, you know, well, I'm not really comparing the efficiency here. I'm just comparing between different architectures. One thing you see is tempting here, you know, to look at GPUs to solve the problem, because you get decent speed-ups in both types of the computation. However, only if you can leave the data on the GPUs. As soon as you have to include the data transfer between CPUs and GPUs, of course, there is no point in adding a GPU. The motivation to add the GPU is GPUs, you know, may have high peak performance, but that's not what we are interested in. We're interested in the memory bandwidth for the dynamics. Okay, so the message is basically if we can leave the data on the GPUs, this is an interesting architecture to look at to speed up these computations and make them cheaper. And it turns out we can, because the memory footprint of the code is very small compared to, you know, what other people might be used to from material science or chemistry. It's only on the range of tens of gigabytes. So you could fit the whole problem on even a few GPUs if you then have enough bandwidth to provide time, you know, the solution in the required time. Okay, so going back to the code, what then this team did is basically made a decision to, and this was purely based on technical considerations and also social considerations. To technical considerations favored rewriting the dynamical core in C++, but social considerations led us to conclude that we have to leave the physics part of the code in Fortran, because this is what most of the user community is dealing with, and you don't want to rewrite the code and nobody understands the code anymore that they've been using for the last 15 years. You have a lot of unhappy people that you create that way. So, so essentially, the plan was to do a rewrite and here an adaptation, write a code that works both on CPUs and GPUs with the same code basis. This is done with CUDA for the GPUs in the dynamics, and with OpenACC for the GPUs in the physics. I will make a few remarks. I won't go into details of how this was done, just that the dynamics relies on stencils, and it was natural to develop a stencil library for this problem. And the approach that was taken was using template metaprogramming in C++, to do it generally for 3D structured grids, allow parallelization in the horizontal IJ plane, and it's, so you can imagine having this grid of columns, and you multi-thread over the columns, and your serial inside of a column. And then combine this with halo exchange and the domain decomposition over multiple nodes. The good thing about taking this template metaprogramming approach, there's a number of good things, but one of them is it allows us to abstract the hardware and hide the complexity of implementations for CPUs and GPUs. Turns out the implementations for CPUs are as complex as those for GPUs. If you want to get good performance out of Interlagos or of a dual socket Sandy Bridge node, you have to do some work. You cannot just put OpenMP on those nodes and expect that the performance will be good. So the other thing is we can hide the ugly optimizations from the users of the code, and we end up with a single source code that can compile to multiple platforms and even support different data layouts depending on the hardware that we are working with. The performance of the codes, and here I make it explicit, I'm looking at an apples to oranges comparison. When you look at different implementations, different hardware, it's very hard to, you can spend almost a PhD thesis just to try to make an apples to apples comparison, and we don't have time for this. But what we are showing here is speed up compared to the current production code. And the current production code is an optimized code. So it's not, it's a code used by several weather services. So people have, professionals have worked on this. To our surprise, actually, it was, this is the speed up of the current code running on an Interlagos, an entire socket, compared to the new code running on a K20X GPU. One thing that is not showed on the slide is the new code, the new dynamical core, performs almost a factor 2 better than the old code when you just do a CPU to CPU comparison. But that's not our goal. Ultimately, we want to run this on a hybrid system, so this is what we're showing. The dynamics is really winning significantly, and so this factor 4 to 6 here is really coming from this combination of higher bandwidth plus some improvements in these new implementations. I'm pointing this out because this is a C++ code. Most people in HPC say C++ doesn't perform. Well, in this case, it does better than a really hand-optimized Fortran code. For the physics, we just take the current code with OpenACC, and even there, well, here you just see mostly that there is more power in the GPU. And so you see the usual 2 to 3 type of performance increase. So you shouldn't see more, otherwise the old code has not been implemented well on the CPUs. Okay, so that's roughly the performance gain. Now the second part I want to discuss, and this may become a bit more mathematical, but in the end this is about algorithms and mapping algorithms. This is Schrödinger equation that we use in most material science, quantum material science codes. The way it is approached is by now not solving the problem on a grid like before, so it's also a PDE, but it's not solving on a grid, but taking some sort of a basis set expansion of the solutions, the wave functions. This leads then, this operator becomes a matrix. The basis set doesn't have to be orthogonal, so you have an overlap matrix. And the problem we have to solve in most of these codes is a generalized eigenvalue problem. For a dense matrix, so this is the dominant motif, and we typically need of the order of 10 to 15% of the eigenvectors, which are then these eigenfunctions here from which we compute the electron density and so on. So the details don't matter. One important thing is that the typical matrix size is of the order of 10,000 and not much bigger. There's some exceptional code where the matrix goes to 100,000, but in most cases we're really interested in these relatively, I would say, mid-size, small to mid-size problem. And this is a headache for scalability. Okay, so the approach that is taken is to transform the generalized eigenvalue problem with a Cholesky decomposition into a standard eigenvalue problem, and then solve the standard eigenvalue problem So this is the general standard approach in LAPAC. Solve the standard eigenvalue problem by transforming this matrix A prime into a tridiagonal matrix that is then easily solved, and then all you have to do is back transform the vectors, and you're done. So this is a rather straightforward algorithm. The problem of it is that most of the time is spent here in this tridiagonalization, and this is, again, is a BLAS level 2 routine. And if you go back to the beginning of my talk, this is the type of thing we don't like, because it doesn't respect data locality. It takes a lot of data movement compared to the compute that you do. So what is done, and not just in our approach here, but also in libraries, like there is a German effort, ELPA, at Garching, that does a very similar, picks up an idea that it goes back actually to the 60s, to make this step here slightly more complicated, namely split the tridiagonalization up in 2 steps, a reduction to band, and then a tridiagonalization of a banded matrix. And the price you pay is you need to now do 2 eigenvector back transformations. The benefit you get is this is now a BLAS level 3 operation here, and so you increase data locality at some price of compute. But the reason we will win in the end is because we don't have to back transform all eigenvectors, but just about 10–20% of the eigenvectors. Now you can do this on a CPU with regular, based on regular BLAS operations, or you can even do things a bit more sophisticated and go on a hybrid system, namely do the reduction to band for one panel on the, with a QR factorization on the CPU, and then do the updates of the trailing matrix on the CPU, on the GPU, and so this leads basically for this very expensive reduction to band to be running hybrid on a CPU and GPU. And moreover, you can, when you're done with the update of the trailing matrix for this panel here, you can start the QR factorization on the CPU of this panel while you're still working on the rest of updating the trailing matrix. So you can overlay computation on both devices on a hybrid node. And so you end up with a truly hybrid implementation of this solving the standard eigenvalue problem. And I'm just showing some results. This is now taking a size 10,000, so the typical problem we solve, we have to solve comparing to MKL on a 2-socket node. So this is running on two at the time Westmere sockets. And what you see here is that the ELPA library, so this is implementing this 2-stage solver, does as good when you take all eigenvectors, which is not the case we're interested in. The case we're interested in is just 10% of the eigenvectors. And so you can see the 2-stage solver here of this library beats MKL significantly, even on the CPUs. And then by replacing one of the CPUs with a GPU and run on the same node, you can see you get another factor 2 to 3 improvement in performance. And the trick again here is to change algorithms, so you increase data locality in the tree diagonalization and this truly hybrid implementation. So from these examples, the essential lessons that we learned that I want to stress, and I will keep stressing them, is at the time on Jaguar, we basically won because we changed an algorithm to move a rank 1 to a rank K update. In the case of COSMO, we get this factor 2 performance because we are changing pre-computed parameters into recomputing those parameters. So introduce compute on the fly. So increase the number of computations, but thereby reduce the amount of data that you have to transfer from memory to the processor. And some other improvements in the software rewrite to increase data locality, and then take advantage of new or different hardware that is optimized or has better bandwidth. And the eigensolver, again, the same story as in the previous two cases, change the algorithm to go from a BLAS level 2 operation to a BLAS level 3 operation, and this pays off even though we do increase more compute. And it pays off on the CPUs and on the GPUs, or the hybrid implementation. Okay, so I introduced this slide because there's a lot you learn when you work on many applications. I just shown 3, but we had a program working on about on 12 different projects in Switzerland. And so some of the messages that we get out is algorithm redesign is probably the most important thing that we can do to get to exascale. Okay. I know that most other programs and many places, including our center, also have to invest a lot of money in hardware and infrastructure, but the biggest advances that we will get is from investments in softwares and algorithms. And as I said, increasing data locality is a key factor. Scalability has to be designed into the applications from the bottom up. So this idea that you can take a legacy code and scale it is not working in most cases. There may be some exceptions to this rule, but in most cases, you have to invest in really rewriting the software. For the programming models and in environment, what we need is we have complex nodes and we have distributed memory. Previously, we only had distributed memory. Now we have to deal with both things. So we need massive multi-threading on a node. We need to support heterogeneous memory and memory hierarchies. And I'm not saying how you have to do this. I'm just saying this is what we need from a programmer point of view. And then we need hybrid execution units, so latency optimized cores and throughput optimized cores. And everything we do, and this is an empirical requirement, I don't really fully understand why, but somehow HPC is extremely slow at introducing new languages. When I was a student, I was enthusiastically looking at other things, and basically now I resigned to Fortran C and C++. And you know, you get older, you just have to face with reality. And I think we also need tools and mechanisms. So we need continue to invest in numerical libraries, and I think we also need data structure-specific tools and templates or languages. This is also a bit different for computer scientists because we tend to like to think in terms of algorithms, but I really believe that we also need help in dealing with data structures. So if we have all this, so either we have now a perfect programming model, which we may hear in the next talk coming down the line, and then we can sit back. If we don't have this, we have to deal with all these things ourselves. And then the question is, what about the separation of concerns? You want now an application scientist to be a computer architect at the same time. We know that this is not a sustainable model. You may find a few areas like QCD where this is indeed the case, but in most other areas of science, this is not the case. In order to understand the problem, I want to go through quickly the workflow of how you know, these applications evolve. Typically, we start from a physical model that some scientists have in their head. We have a mathematical description of this model. In the case of the weather model, these are the Euler equations they solve for COSMO. But you can put any other field here, and you will have a Schrödinger equation here with some electrons and protons and so flying around. And then, in order to solve this, so this is a continuous set of equations, you need to discretize, and you need numerical algorithms to solve these equations numerically. Then, once you have this discretization and algorithms, you have to implement the code that you compile, and then you run it on a computer. Deliberately, I picked, this is a Cray YMP that the type I was running on when I was a graduate student. And I remember that things were pretty much working this way at the time. There were a few things already that were broken. Namely, we were developing on a workstation, and we had to port the code to the vector machine and vectorize the code. Okay, but then during the 90s, we had to start parallelizing codes, and it was not at all clear how you parallelize codes at the time. Now it's clear everybody does MPI. And so you realize, and now we talk about petascaling, exascaling in place, you realize that something is not working here either anymore. But in this model, the separation of concerns is typically here. The application scientists think about all this here and then write an implementation. The computer scientists think about all the things below. Okay? And this is simple, but it somehow doesn't work anymore. So we have to think differently, throw things out of the past and look at the problem. The real problem we have is we have multiple architectures. And it turns out, depending on the architecture, you have to choose different algorithms and implementations. We also know, scientists know that up here things are not linear anymore either, that typically, depending on what you can do down here, you decide what model you can solve or how complicated you can make the model. Depending on the methods you have, that may change the model again or again. Depending on the algorithms, you may change the method, make these a bit more sophisticated. So there's an iteration here, but most importantly, there's an influence depending on the architecture, what algorithms you choose and what implementations you choose. And this is, of course, if you care about performance. If you don't care about performance, then, you know, the world is much simpler, and you can use MATLAB or for simpler problems or so. So then don't worry about this. But if you care about performance, this is really what you have to deal with. And it's easy to write down this diagram. It's not easy to now say how we separate concerns. Naturally, it would be to draw a line here. But then do you really want people who understand everything down here? I think we've not made much progress either. So one thing is to just look at who are the natural drivers. One is the scientists who take care of this up here, and then the vendors who take care about this down here. And the trick is to not to forget about these things in the middle. But the question is, how do we do this? I'm not saying that I know the answer. Okay, but I think we managed in the last 3 years that we've been running an application-oriented program in Switzerland. We learned a lot of lessons, and I'm taking a simplified view of the software structure of this COSMO code. You have typically main. We have again physics, dynamics. We have a few other things that I'm ignoring. The dynamics is domain decomposed. You build on MPI, and everything is built on top of a system. This is the current production code. Rather monolithic pieces of codes here. And this is the new code. After we did the refactoring on the dynamics, you see now on top of MPI, we have a generic communication layer that actually builds on top of MPI, but could build on DMAP or on other things as well. we have something that takes care of boundary conditions and halo exchange. We have the stencil library I talked about, and we have the dynamics. So once you look at this structure and you realize that these things are now not specific to this code anymore, but they are specific to the domain. And we even have the fact that the hardware now is encapsulated inside, for example, this stencil library, and we have well separated the node hardware from the communication between the nodes. You can see that rather than drawing a line just where the colors are different here, we can now draw a line and have, we can have, like in the past, the system, the basic libraries, which is MPI here, but it can also be basic numerical libraries. And then we have introduced a stack in the middle that I now call domain-specific libraries and tools. And this includes domain-specific embedded languages and all these things. Okay, so it's a little bit more general. And so this is what we have to figure out, is how to maintain this software stack in a professional way, and how, and we even believe that some of these tools will be more general than a particular domain. I don't think they are as generic as the ones we are talking about down here. So the way we are going to approach, as I said, I don't believe that this is the, fully understand everything, but I think this is the direction we have to go into. So in Switzerland, what we are now going to do in the next 3 or 4 years is with a new program that we call Platform for Advanced Scientific Computing. We will fund co-design projects that will be concerned with creating these types of tools. They may fund a little bit application development and even some developments at the levels of the compilers, as long as they are open source, and but mainly focus on these layers, and probably develop in a number of areas domain-specific libraries and tools. This is just to show you how things are progressing here in Switzerland at CSCS. We just completed the new building last year. We also completed this first investment in software development. And of course, our production current flagship system is a Cray XK6. We are in the process of building a next generation of systems at CSCS. And we are, since this was considered a rather successful program, we managed to secure funding for the successor, which is this Platform for Advanced Scientific Computing that I discussed before, and is going to now look at how to deal with co-designing these various software layers that we need between the application and the various types of hardware. So we have no ambition here to design hardware. We are taking for granted that GPUs develop, mic develop, and CPUs develop, and are driven by markets that are much, much bigger than funded, and driven by markets that are much, much bigger than HPC. And then, of course, we are also even starting to talk about what things have to look like towards the end of the decade. This is briefly the acknowledgement of the rather large teams between the various application efforts, and that's the end of the talk. Thank you.